Welcome to the embedded app of the day. Today I'm going to talk about a consumer product. So what do you think this is? Let's see. Digital photo frame. Have any of you seen these before? All right, so let's take a look inside this wonderful box and see what kind of wonderful things you can find inside there. All right, of course, it comes with its own CD. Yay. And, oh, apparently this didn't come to, they had some problems shipping this from the manufacturer, right? Oh, my. As it turns out, my wife's aunt had this in her home and used it for many years, and then it kind of failed. Actually, no, it failed after a year and a half or so. And
Did you get the grade?
they just bought a new one, didn't bother to look at it in more detail. So let's take a look at what is inside of this device. As you can imagine, you've got your mechanical enclosures. So we'll just kind of ignore those mechanical enclosures for now. But there is one enclosure or one part of this mechanics that I want to show you. And that is this little device here. So this is, as you can tell, what? Looks like lots of buttons, right?
Yeah.
So what you have here at the bottom is ways to actually go through your digital photo album. And of course, there are other things that we're going to look at here, but notice how the way they manufacture it is that this card is going to be put into place here, and then the buttons will be pressed, and here is the signal for the buttons. Notice that the number of connectors here are, I don't know if you can see that in great detail. Electrical contacts, there are focus. And probably can't handle that high. There's 5 on this side and none on the other side. But look at that. There's 1, 2, 3, 4, 5, 6, 7 buttons. What? How do you think they're doing that? So, you never know when a concept will show up on a test where you ask concepts like, how can you encode multiple button presses on a single lesser number of lines? So if you look very carefully on this board, I don't see any active component here, and on this one, the only devices that we have other than the switches are resistors and capacitors. We have a couple of things here that say diode, which may actually serve as transistors because they have 3 feet on them, right? So you never know when we'll ask on a test how you do that. So let's take a look at some other wonderful pieces here. One thing I do need to also point out, oh, by the way, this is the LCD. And this is what you're paying all the money for, is the LCD that will be a certain resolution. And if you look very carefully at this cable right here, this cable has vias, which is rather interesting that some connections are going through this plastic to the other side. And if we were to take a look at this connector right here, notice that there is something here called Kapton tape, which is over these connectors. And this cable actually slipped in. Ooh, I may not pull this out and have it live. There we go. Disconnected. It has connections on both sides. Oh, just one side, then we'll get it. Just one side. So I guess some of these connections come from the other side, and then they're routed across to the front. So this is only one set of connections, not on the other side. Not on the other side. But notice that this is an entire assembly. So they probably buy this from somebody, in fact, here it is. They buy it from a company called Inolux. And they buy that and they put it in their own products. So let's take a look at some features of this. Number one, notice that this squishy little thing here is silverish. And what it's being used as a ground, because you notice that this silver stuff is soldered to a large pad right there. Often they use this for serving as some sort of signal ground, not necessarily electrical ground. And they have several of these all over the board. Now, probably prominent to this that you've noticed are a couple of parts. So here's one. AM logic, and I looked this up, and the AM logic processor is a device, and I actually contacted the manufacturer of this entire device, and he came up with a description of some information about this. So the company AM Logic, if you look at this carefully, it's a complete integrated system targeting digital picture frame market. And the interesting thing about this is that it has a whole bunch of things on the chip itself. Not necessarily all of them are being used. For example, if I look carefully at the screen, since there is a piece of plastic in front of it, this screen can never be touched. So obviously this is not a touch screen. However, it allows for a touch controller. So that means that this chip that has been manufactured and put on this board actually is not specifically for this picture frame only, but is for a whole bunch of different picture frames. You don't have to use all the functionality of the specific chip. What else does it provide? Well, 32-bit. That means it's a big processor. It's got a heck of a lot of pins, 216, and if you notice, they're on the outside. It's a lot cheaper to manufacture a quad flat pack than it is a ball grid array. Remember ball grid array, the connections are on the bottom. And then he goes into a little bit more detail, a base operating system, what it looks like they provide it with the chip as well. They also have drivers and everything else. So what it looks like is this entire product is based around this specific chip, and that specific chip also provides all sorts of I/O that one could ever need. If you look at the back, look at some of the I/O that you have right here. Here's a USB port, so you can stick in a USB key. Here is a memory card interface. Here's another type of memory card interface. They're a little bit older. Let's see if this switch, this power switch, yeah, the power switch on the back is actually accessible. Interesting enough, look at this. It also has the small mini programmable USB right here, and of course here's where you can put in your power. So this USB port right here serves as this device is the master, and the memory stick that you could you store your 8 or 16 gigs on is a slave device. This device right here, this specific port indicates that you're communicating via a PC, and this board is the slave device when you plug into this. So again, here's some more information. It does really good with JPEG screens and it could actually, in fact, this guy, when he responded back to me, it's from the user guide, so it's a whole bunch of stuff. Talks about the touch controller, the processor, clocking functions, Bluetooth controller. This thing has a whole bunch of stuff on it. High-speed UARTs, goes in more about the operating system. So that is a rather interesting aspect of this. There's another really interesting chip here. You zoom in right here. It says Toshiba, and it has a whole bunch of numbers. And so what I did is I looked up, and it's amazing what you can find on the internet. So this Toshiba part, which you can imagine, is I like this, Toshiba Confidential, and I pulled it off the web. Is a 16 gigabit, that is a 2 gigabyte memory storage device. So they have 2 gig of onboard storage for this microcontroller. So this 2 gig is most likely going to be for the either just the software alone or for the software and images. If I were to bet, I'd say it's only for the images, and I would bet that the firmware itself is on this chip, which I think they also alluded to in my email. Let's see if I can see how much they provide on it. I can't find it off the top of my head. I gotta believe it has some memory on it. So this just tells you a little bit about that other chip. I actually looked up this Ring Bond one, and I could not find any references on this. But the other thing you can take a look at is, of course, a rich set of I/O, which gives its own problem because each time you have external I/O, you have to have some way to protect yourself from it. And I'm looking over here. This indicates what? Oscilloscope. Or an oscillator, sorry. It's not an oscilloscope. That would be silly. All right, so what it is that this is a specific embedded board that is used for a picture frame, and most likely this board has been manufactured for use in other types of devices with other types of connectivity. Because if you look right here, there's a whole bunch of pins right there that aren't even used. There's a whole bunch more that are used. There are more down here that aren't even used. And there's a couple other pads around here that have not been identified or populated yet. So what it turns out is that this is a board that could be used in a couple of different products, maybe different ones that are more and more expensive. And so very often one of the tricks of a designer is that he will design one board to be used in 3 different products, and then based on how you populate the parts on here will be how much that specific one costs. I'm looking to see if there's any other parts on here that are not populated. That's about it. It looks like everything else here has, most of the major parts have been put on this. All right? So this is today's app of the day, which is the Insignia digital picture frame.
Is there a remote control as well?
All right, welcome to Embedded Systems. This is, I believe, lecture number 27. As always, your mileage may vary. Make sure you check the notes. So today, I'm going to go into a little bit more detail about what an operating system will do for you. Specifically, we're going to go a little bit lower than what you're probably used to in your Windows operating system or something like that. Because when you're an embedded system, what's one of the biggest resources you might want to share? What was that?
Memory?
Memory. That is exactly right. Memory, in particular, specific variables. For example, if you have multiple processes and multiple threads running, you will have the situation where some bit of memory is shared by a whole bunch of different processors. Have you seen something like that? That could be an example of that in one of your previous labs, for example. How about the queue? You have serial data coming in. So you have the interrupt service routine grab that data, and then perhaps you have another process that will consume all of these characters that you pull in on a serial communications port. So we're going to look at a little bit more detail about how you can share things like that, and we'll go into that in a lot more detail in Advanced Embedded. So, first of all, we're engineers, and so we're very safe people. So we have to keep in mind that when you start sharing things between people, you have the problem of other bugs that might come up. Just like if you share a glass, you're all going to get the flu virus, right? When you're sharing memory with other devices, you may have problems associated with these threads or processes wanting to change that same variable at the same time. And this is identified with some general concepts of how the data is gathered. So you're aware of the concept of registers, right? That's one level of memory. And these would be the data registers inside the processor, not the peripheral registers. Now imagine, and I think I've talked about this before in class, but if you have a situation where you have data showing up in several places, for example, you might have a hard drive, and some bit of data is stored there, and then you have your main memory, and you pull this bit of data into your main memory, and you use it because main memory is a lot faster. And then when you do an individual calculation inside of your, what does that look like? ALU, or as I call it, the pair of pants, right? All right, thank you very much. I'll be all week. Does that look familiar? Yes? This should, okay, everybody who took computer architecture, you know what that is, right? You're pulling data from a register, you're putting it through your arithmetic logic unit. That might be an addition. Your result is then put back into a register. And oh, by the way, that one particular value may be put into that register. And if we get into different types of computer architecture, we may make it even more complex. We may have something in the middle called cache, where you copy a chunk of memory into cache, and then an individual value gets copied into a register. Now the big problem comes down to, oh my, this same piece of data could exist on the hard drive, in memory, in cache, in a register. And how do you ensure that if you make a change here in the register, you do an addition and then you put it back in the one specific R1 register or D1 or whatever the name is for your system? You have to make sure that that will, oh, there's no color. That particular value will get written back to the cache, which will be written back to the memory, which will be written back to the hard drive. And how do you ensure that that value isn't different in all these different places? Because what could happen? What is the one big interrupting thing that could happen that might change this at any time? I said it earlier. Interrupting thing, right? an interrupt, right? An interrupt might occur, and in the interrupt service routine, you can change something. And how do you know that it's the correct value here, or is it here? Or is it here, or is it here? And so that's the big danger, is what we call data concurrency. It could exist in several different places. So we have to make sure it is the most recent accurate data possible. And that if we're doing any changes, maybe instead of allowing an interrupt to happen, maybe we should say, no, interrupt, you'll have to wait until I've fixed all my memory problems up there, or my concurrency problems. So, what it comes down to is the compiler is trying to be really nice to you and make things run really fast, so it doesn't necessarily reload the value from memory every time it wants to use it, but anytime you change threads or processes or have interrupts occur, it may actually be changing in those other areas. So the problem we have to do is rely on our operating system to identify that data which is shared by many different processes and many different threads, and ensure that you do not change anything if somebody's actively working with it. So that's the whole premise of what we're doing, so let's get into the details. First of all, we have to identify a piece of data as volatile if it's changing. Not if we're just reading it. If we're just reading it, do you really care if you're only reading it and you're only gathering the information from it, like a constant is a good example, all right? So a constant exists here, and what's the whole idea of a constant? Does it change? No, that's why it's called a constant, right? So it exists here, it's the exact same value here in memory. I'm not going to confuse life. I'm not going to have any cache in my system. So the same value is here in the hard drive, it's here in memory, it's here in the register, same exact thing. Do we care? No. It's only when that value changes and it becomes volatile. Volatile meaning changing, right? So in this case, maybe one thing we could do, and by the way, since we're running with an embedded system, I'm going to assume that we don't have to worry about a hard drive either. That makes things a lot easier to manage. Now you only have a situation where something exists in two places, either in the register or in memory. So I'm going to ensure that anytime I use a piece of data and that I change it, that I ensure that nobody else can touch that piece of data while I'm using it. And one of the easiest ways you can do that is in your compiler to identify a specific variable as being volatile. Volatile means that you have to address that particular storage of that variable before you can address an interrupt or move to another, move to another thread or process. So in that case, you have something called the Volatile Directive. You know, int volatile, volatile int, star, variable, whatever. And the nice thing about that is, usually what that means is the C source code, when it's converted into the assembly language machine language, will never store it in a register. It will be a single instruction that is only used by the assembly language instruction, and from that respect then, you cannot interrupt that assembly language instruction, because interrupts must allow the current instruction to complete. So this means that a particular variable will never go into the register. It will always be used from memory. Now, very often, you have something that must be shared between processes, and both of the processes could change it. So now you have a problem of, I'm trying to think of a good example of this. In fact, I'll have an example of this in a few minutes, and we can look at it. But let me do some definitions first, all right? So we're going to have some cooperation, but anytime you have cooperation and coordination, you're going to take more time. So again, all of these operating system possibilities are going to take more time. So I can do one of two ways of sharing information. I can actually have a single space of memory shared between two processes, so it exists in the same place, and the two have to coordinate as to who has access to it at a time. Or they could specifically send a massage. They can send a message to each other. Now, in the world of shared memory, that's really easy. When all the processes have an easy access to these global variables. Now, when you get into Unix and other high-end embedded systems, then you have the problem of, here's a memory area. Do you allow all the processes running to touch that one single memory area? Or do you have to call some of these memory areas, what's the best way to put it? So process A and process B are restricted from touching each other's memory. In other words, you create what's called a memory protection fault. I'm sure you've seen that in the old operating systems. In other words, one process can't touch the other process's memory because there's no good that could ever come of some process messing with somebody else's memory. That would be equivalent to everybody doing their homework here in class, and somebody has the ability to walk up to your homework paper, erase one of your answers, write in a new answer for that, and then you have to turn in that assignment for grading. Does that sound fair? Unless the person is really good and you're not really that good, right? That might be fair. No, that's not fair. Because what they may do is just mess it up altogether. And usually, when one process messes with another process's memory, it's not, oh, I'm going to put a nice value there. That pretty much will work. It comes down to one process is out of control and it's just writing all sorts of junk to memory that will never stop. It's basically overwriting everything it can get its hands on. So to prevent that, let's say we can have message passing, and you can only use message passing to pass information between two different processes. The problem with this is that it's very expensive. Expensive meaning it takes a lot of software and a lot of instructions to put it into place. This is often what's called a mailbox or a queue. So let's take a look at one little example of a shared data problem. So in this case, I'm going to run these two processes, and in my case, remember, an integer is 16 bits. Now I can create a long integer, which is 32 bits. In the case of my unsigned integers, which is going to be associated with, let's say, a time tick, right? And so we have our time tick, the high byte, or the high 16 bits of it, and then we're going to have the lower part of it. So whenever I get a timer tick, here's what happens. I have this nice little interrupt, and it will take, I guess, well, here it is pretty clear here. So in the case of my timer tick, I can only work with 16 bits at a time, but I want to accumulate it into one big, long 32-bit number. So I split it into two parts. So every time I have a timer tick that is generated by my hardware, I will increment this variable TC. And if it just so happens that I go from FFFF to 0, then what I do is I increment this. So the real reasonable thing that would happen is this would be 1, 2, 3, FFFF, 1, 2, 3, FFFF. And then if I increment and get a timer tick, well, it should become 0, 1, 2, 4, 0, 0, 0, 0. Does that seem reasonable of what should happen? Well, here's what could happen if we allow an interrupt to come in at any time. So here first thing we do is, oh yeah, we want to represent this 16-bit number and this 16-bit number, concatenate them and represent it as 32 bits. So what we'll do is we'll copy over this first part into our variable. And then remember this is shift 16 bits over. So the next thing we'll do is we'll shift it 16 bits over. Then, oh, what do you know? I get an interrupt. And it so happens that my timer's counted down and it's time for me to increment the timer count. And so I increment my timer count. F now becomes 0, 0, 0, 0. And then according to this, if that happens, then I'm going to increment my TC high. So at this point, TC high is going to be what? 1, 2, 4. But remember, I've already counted, or I've already moved over the value of 1, 2, 3 over to my 16, or over to my 32-bit number. Now I've done this interrupt service routine. I return back to the next instruction, and as it turns out, then I'm going to move this value over here, and so I have the accurate time, right? So what's the big problem with this problem, or with this exercise right here? So what are my solutions? So what I would like you to do is, between you and the person sitting next to me, give me a list of at least 4 things I could do to prevent this from happening. All right? And I'm going to call some of you as we go along, so there's no hiding. You have to come up with at least one solution. All right? You pause. All right. So, as a part of this, we were going to ask, what are some ideas? Give me some ideas. What can I do?
Set a flag that'll bypass any other service routines and keep it inside that one.
Ooh, do a flag. How about this? Disable interrupts.
Yeah.
So, somebody said disable interrupts while they're doing it. Okay, that's a great idea. How many of you had that idea? Yeah, okay. Somebody in the back there with the knit cap, the toboggan. Yeah, you. What is your idea? No, that's not a toboggan. That's a nice hat. The one behind you. Yeah, you.
I got nothing.
You have nothing? You have nothing for me?
No.
Oh yeah, all right. Just go right up there. Yeah, but you had more than one idea, right? Anybody else have any other ideas? Yes. What if you do what? Oh, back up. Temp variable. That's interesting. Back up the idea of the temporary variable. How about another idea? Let's show this back up. Yes, yes, sir.
Use a lock?
Use a log anyhow, right? Well,
No, a lock.
a lock. Oh, use a lock. Are you looking ahead in the notes, or you just came up with that on your own? How about this? Where's the most critical area here? So this looks to be like the really critical area here, right? How about this? What if you do it twice? What if you do this once, followed again by this, like you did, 10 people chai, and you shifted it over, and then you did it again and shifted it over. Would that work? Well, in this situation, it would, wouldn't it? There might be some extra code, right? So I'm going to add to my list, do it twice. I mean, it's just an idea. It might be crazy, right? But hey, it might be interesting. So let's take a look at, for those of you who actually pulled your PC up and are looking at the notes that are available. The whole idea is what I'm saying is that if each one of these instructions is atomic, meaning that you cannot interrupt while it is running, this instruction right here is atomic, this right here is atomic, but this whole entire subroutine is not atomic. In other words, it can be interrupted at any time. So one of the ideas somebody came up with is perhaps it's so critical, these group of instructions must be executed as if it's a single instruction and basically turn off interrupts. So let's take a look at some examples. So what you're going to find is in the cases of our operating system, these will be race conditions. In other words, where you run it one time and you'll get one result, and you'll run it another time and you'll get a completely different result. And that is because it is very time dependent of what happens. And that is something especially characteristic of operating systems, or I should say of embedded systems, that are relying on the clock for something going on. So, let's look at some definitions. Number one, a critical section is what we call a non-reentrant, meaning that it can't be called twice recursively or anything else like that. That it's only executed by one process and only should be executed by one process at a time. So you need to implement some sort of lock. We had an idea from somebody else to be able to enter and exit this critical section. And this lock might be nothing more than turning off interrupts. Oh, by the way, the concept of non- or re-entrant code is it could have several it could have multiple simultaneous invocations, and they don't necessarily interfere with each other. Now what that means is that there's a piece of code that is reusable by different processes. And this is very common. You only need to write a subroutine once, right? You just call it several times. One example of that could be printf. Printf only exists in one place, right? But several processes could call it at about the same time. So the nice thing about that is that when you're doing that, reentrant code is not going to rely on global data. And so that means that if the code uses global data, then it's non-reentrant. And the other thing that we saw is a race condition. This previous problem up here really depended on where this occurred. So if the interrupt occurred, for example, right after one executed, would you have the problem? Yes, right? Because this already occurred. You already moved it over. What about if it occurred after 2 executed? Do you have the problem? Yes. Would you have the problem if the interrupt occurred after this line right here executed? Who says yes? Raise your hand. You gotta vote yes or no. And if you don't raise your hand, I'll tear up your quiz. All right. So who says that if the interrupt occurs and is executed after this instruction, you have no problem? Who votes yes on that? All right. Who says no? You have a problem. Who doesn't know what the heck is going on and you want to raise your hand because you don't want your quiz ripped up? All right, the answer is, where's the last place that you actually touched this variable? Right here, right? So if it so happens that the interrupt occurs after you execute this, will it be exactly up to date? And it won't be exactly up to date because you'll be returning the value of 1, 2, 3, F, but at least it won't be badly wrong. In this case, it's badly wrong because you have 1, 2, 3, 0, 0. Oops, there should be another 0 in here. In fact, I always have this problem, so what I'm going to do is, I'm going to fix this. So what we will see is if your interrupt will occur and at least this instruction completes, you are technically correct, although a little bit outdated. So let's take a little look at assembly language. This is where you ET guys will have more familiarity since you've played with this before. If we have a long integer and we are incrementing it, what actually happens? Well, in a processor that has only 16 bits, of course this won't be a problem with the 32-bit processor, but with a processor with only 16 bits in a register, your problem will be that you have to add a single variable. And in fact, maybe I should mention this because this should have been in your computer architecture. In your computer architecture, let's say you have data register 0, data register 1, data register 2, data register 3, and these are only 16 bits long. And they are only 16 bits long, so if you want a long word, what they say is that your long word will really be, you'll take your data register 0 and your data register 1, and you'll configure it side by side. And it depends on the processor. Sometimes it's D1, D0, but in this case, we'll call it D0, D1. So in this case, we have 2 registers, or actually these are 2 memory locations. So in one memory location, it's going to add a 1, and that would be to the high part of it, and then in the lower part of it, it's going to increment. So what you'll see is, in this case, if you are doing some operation in the process, so you've done this add right here, and then suddenly this instruction right here is going to execute, what's going to happen? Well, since this single instruction in C does not represent one instruction in assembly, but it represents 2, you will have the interrupt occur, and the memory location will be changed by this function right here, and then when you return over here, this will be incorrect. And so this race connection will be due to the fact that this single C instruction is not atomic. And that happens when you're working with data structures and large variables. So, we've seen this before. Remember that Q example for the serial communications? So when I said Q is going to be incremented, or the size of it is going to be incremented, it actually comes down to a total of 3 or 4 instructions. In this case, you have a frame base, which is pointing to memory, and then you will finally, at this point, you will add what the value is. And the same with decrementing. This is why, even though this is a single C instruction, perhaps in some cases you need to disable interrupts in some very critical part, because one C instruction is expanded into 4 or 5 assembly language instructions. So here's one solution, which was brought up by Mr. Morgan in the back, and that is disable interrupts. So by the way, you know that you can embed assembly language code in your C, right?
Yes,
So there you go. We're saying we're going to run this assembly language instruction, and that's the specific instruction we're going to do. And it just turns out that fset is a typical assembly language instruction which says set the flag bit, specifically the I, or set the flag register, specifically the interrupt, enable, and disable bit. Set means set it to 1, clear means set it to 0. And the interesting thing about this is, so here we go. We can use a pound define. This is a neat thing. So this is really readable. All right, disable the interrupts and then enable them later. So this looks pretty good, right? Will this work? Do you see any problems with this at all?
You might miss incrementing something.
Say that again?
You might miss incrementing the tick one time if they're.
Now, let's make the assumption that the interrupt service routine is not called that frequently, and at least you can get through those 3 instructions, probably a lot more. So, yeah, that's a great idea. That's a great observation. You know what? That's such a good observation, I think you need to get a trip to the price closet. But there's another problem associated with this. What do you think?
If the access is temporary,
If it accesses what?
it can be registered.
If it does accesses the what?
The EMP register. Before it becomes temporary.
Nah, that's not quite it. What about if interrupts were already disabled anyhow? What if a part of the program that's running disables interrupts anyhow? And now suddenly you have disabled interrupts. Oh, that's no problem. They were already disabled. But now, unexpectedly, you're enabling interrupts. So in other words, the previous code that ran, or I'm sorry, the code that was running just earlier before this was also critical. And somewhere later on, you were going to enable interrupts. So, whoa, that doesn't work out too well. So suddenly you may enable interrupts and then all hell may break loose, right? So maybe we need to put in place a concept or an idea to say, all right, let's check to make sure that interrupts are not currently enabled. And if they're not currently enabled, or if they're not currently disabled, then we'll go ahead. So look at this. There's more assembly language. I love this. This is real computer engineers programmed down to bare metal, by the way. So just remember that. So in this case, we have set up a mask. We're going to do some operations. So this simply will say, let's look at what the current state is. let's grab it, let's look at it, let's store it, and if the flag was already disabled, then don't touch it. But if interrupts were not currently, or if interrupts were currently enabled, then it's okay to renable them because here you disable them and here you're enabling them. So this is a way to be able to survive this. Oh yeah, and there are some other types of things in here. You could take a look. You actually, this is all in a pound define. So, oh, excuse me. So it is both this assembly language instruction and the C instruction that you could pound define. And it makes it really readable. If we were to put this in here, it might be a little bit tough. Well, that works out pretty good, right? Is there a problem with that? Well, here's another possible solution. And this is, let's see, somebody come up with this. Backup data in a temp variable. So this is kind of like what you were covering. Did you know that because you looked ahead in the notes? Whoever said that? Did you look ahead in the notes? Oh, good. At least you're not lying, right? So, I kind of alluded this to as well as, so what about if you do it twice, right? So here we did it once. We did this code, we saved it temporarily, we moved it over, we incremented it, and then what do? We do it again. So we save it temporarily, and then we do it all over again. And then we compare the two. So the whole idea is that you stay in this little loop here until you get the same answer both times you do it. Does that seem like a lot of extra computation to do? This works with one assumption, and that is that this code that you're doing in here will take a lot less time than the frequency of a possible interrupt. Because if you're continually getting interrupted and this TC is considerably is being updated every single time, you will never get out of this loop. It will be like an infinite loop. But the assumption with all of this is that you're only going to be running it a few times. Maybe you'll be in this loop once or twice, because you don't really need to do it more than once or twice in quick succession. So you'll have some extra computation, you'll have some extra space taken up by this, but at least you'll be fairly accurate. Big problem is the compiler may look at this and say, that's just dumb, I'm going to take it out. So again, you know, what if TC changes just so frequently? Well, here we go. What about after disabling interrupts, you do the ISR, or you do the work again if it's needed, right? And so this is kind of like a variation on that. You disable the interrupts, and then you enable interrupts, and then you do the important work outside of the interrupt. But at least you read both parts of it. So you read the low part and you read the high part. And then you can do the computation in the end. So that may be a neat thing. So here is your critical section in here, reading and reading. Actually, for all intents and purposes, all you would really need to do is to read TC and TC high, and then re-enable the interrupts. You don't really care about this in the end, because you're close enough, right? And then the final solution, actually I would make sure it's the final one. Yep. The final solution, let me make sure if I really am, is that you use a lock. In other words, if you want to touch this part of the code, then what you have to do is you say, can I have access to the code? And if you've granted access to the code, then you work with the code. You do whatever you need to do with that specific variable, and then when you're all done with it, then you say, now anybody else can use it. And so that's the whole premise of everything associated with our next lecture. Thank you very much.